Hey, it's working. Good afternoon, everyone. May I have your attention, please? Our speaker today is Ian Morrison, who will speak to us about electronic paper. Ian Morrison is a lecturer at Harvard on soft matter physics, a lecturer for the American Chemical Society on colloid chemistry, and president of Owen Research, which is involved in inks for electronics. Previously, he was a fellow at Cabot, Director of Ink Technology at E-Ink Corporation, and a Principal Scientist at Xerox. He has co-authored 2 textbooks on colloid chemistry and has been granted over 50 U.S. patents. Please welcome our speaker.
Thank you, Alex. Okay. Thank you very much. It's a beautiful trip from Cambridge to Hanover. I'm sure all of you have taken this trip, or at least most of you. And it's a lovely countryside, but something you might not have noticed that I noticed yesterday, it's slowly uphill the entire way. You noticed this. It's the grandest feeling to come for a couple hours or 3 hours, gradually up and up a hill. It's an exhilarating feeling. Always going up the mountain is exhilarating. And so as you go up a mountain, of course, and you get in contemplative mode and a relaxed mode and maybe a big picture mode, I find coming into Hanover in these conditions just fantastic. I am thrilled to be here. It seems, to me right now, it seems like a time to think a little broader, a little calmer, a little more challenging than we normally have. And so this, I hope I can contribute a little to this. It sounds like you have this regularly, and for that you should be very happy and proud. It's an excellent tradition. So thank you for having me here. I'm pleased. I want to tell you a little bit about electronic paper, and let me tell you what I want you to remember from this talk, and that is electronic paper will be very, very, very good for you, A. B, we do not have it even slightly yet. And C, it's up to somebody in this room to make it happen. And I'm not kidding. I teach classes at a school, a very good school, like this very good school, and I tell my students, I expect some of them to win the Nobel Prize. And I do. I want them to win the Nobel Prize. I want one of you to win a Nobel Prize, for that matter. If you can't, inventing electronic paper would be good enough. And when either you win the Nobel Prize or invent electronic paper, I only ask one thing, that when you get the great accolades, you mention my name. It's Ian. Try to remember that, and then I may be in my dotage when you do it, but I want to hear about it. So I am serious when I tell you what we do know and what we don't know. I'm serious in the fact that I expect you to be able to do some of this, if not all of this. So I'm going to lay out the questions for you and tell you a little bit about what we do know. More importantly, I'm going to tell you what we don't know. And lastly, I really want to get someone interested enough to give it a shot. This will not be easy, okay? But that's what I want you to remember. The rest is detail. My thesis advisor at Rensselaer, good news and bad news. The bad news is he died just a few weeks ago. The good news is that he was 98. I always check the obituaries to see how people in colloid science and soft matter do. And the average age is quite long, so I'm pleased with that. One thing he could do until the age of 98 is he could quote poetry. Long, long bits of poetry, and he would quote this one to me occasionally, and I rather liked it. It was written by the students of Jowett as a tribute to their professor, because he's a very popular and scholarly gentleman. So it's a little one. And we're going to I want you to read this maybe to yourself, because we're going to come back to this. And the idea that the professor knew it all, of course, is a nice pretext, a nice assumption. You probably discovered that the professor seemed to know most of it, but maybe not all of it, in any case. And I copied a little picture that was on the webpage, of course, next to Jowett and this little poem, a ditty. And I noticed something in the picture, that the man who knew it all was still carrying a book. Small things in life, just small things can hit you, and they just say, that's an interesting thing. Even if you know it all, you want to carry the book. And why the book? And why the book? And you all know it's that tactile connection between what you don't know and where you might find something. It is something glorious about just physically opening a book, paging through, reading what's on those pages. And I want to talk to you a little bit more about this in the next few minutes. But there's something personal about having a book. The book you read can be seen by people around you, and don't you have that look what I'm reading kind of feeling sometimes? Or maybe quite the opposite, or, trying to keep the cover hidden, because you're sitting out here, should be listening to me, and you're actually reading something much more interesting by Peter Drucker or something like that. But in any case, it's not human, but it's kind of personal for us in any case. But we'll come back to this a little bit later as we go on. I want to tell you what we expect about books and newspapers and things like that by making some little comparisons. And this first one I dug out. We start off, the earliest writing was probably on cave walls or stones or something, but we'll pretend the earliest writing were written on rocks. 10 Commandments come to mind. I love the movie. We all have seen the movie, Breaks the Rocks, There were actually 15 commandments, and he lost 5 commandments. But in any case, he kept the 7th commandment. Too bad. You can check it out later on. So writing on rocks, we start off. It's not so very convenient, right? And maybe we could say that the next evolution was to write things on a scroll. Scrolls are quite ancient. This happens to be a copy of a Dead Sea Scroll, you might know. In Palestine, they dig these things up. They're several thousand years old. They contain stories, essentially religious tracts of various kinds, but written out in a scroll. And you can see there's this huge difference between having a rock to carry around, which is useless, and a scroll. So the invention of the scroll is an invention of almost unmeasurable usefulness, and just a glorious step. Huge step to make the scroll. So we could maybe pretend this is Confucius's writing, trying to be politically correct as I possibly can, which I generally fail, but nevertheless. So there's scroll. And then the next step is the Gutenberg Bible, picture of the Gutenberg Bible. Oh, by the way, can anyone in this room name a book, not the Bible, that Gutenberg printed? That's a take-home problem, by the way. Did he only print Bibles? I won't even tell you the answer to that. But anyway, it's a copy of the Gutenberg Bible. And why is the printed page in a book so much better than the scroll? And you can see right this. So you're saying, I read something about something. Where is it on the scroll? Roll, back and forth. But in the book, you go flip. It was on the left-hand side near the bottom of the page, and I remember there's a picture of something on the other side. So you have memories of books you read. You can find things in them. You might even underline or something like that. So finding information in a book is ever so much more useful than the scroll would be. So would give Gutenberg the credit, but of course it's due to many other people. But we went from scrolls to the book form, and now, of course, we have replaced the Gutenberg Bible with an electronic form. It's an iPad or something like that. And so we have this transition. Now, what does the iPad bring to the system is something very interesting. Is that inside the iPad, we have the Gutenberg Bible, we have all of Confucius's writing, and we have the 10 Commandments, and all the rest of the stuff in it. So inside this iPad, we have just an enormous amount of information. And we give Steve Jobs maybe the credit for this. So you could say, in some sense, that we've made these epic steps from writing on stone to writing on scrolls to writing on individual sheets to putting everything electronically in the electronic book. And so even though it's only been 400 years, a little less, 400 years from the Gutenberg Bible, a little more, I should say, 400 years of the Gutenberg Bible until you get to the e-readers and electronic books. It's a huge step. And what are we to complain about something like that? I mean, how could any sensible person say, it's not good enough? And so what I'm going to try to tell you is, it's not good enough. It's a dream that's been lost. Because what we really wanted, and I'll try to make the case for this, is we really wanted the electronic book to feel like the book, to flip the pages like the book, to show people what we were reading, to share, to look maybe in a bigger space. And for that, we need the electronic paper. And so we'll talk about the electronic paper. But you get the general idea. Hope you get the general idea in any case. First thing is about this little transition, is that there's subtle transitions on here. And here's kind of a funny one. We didn't like the tablets. I mean, they were hard to hold on to. They were heavy and stuff like that. They were, as you might say, hard as a rock, right? And then we got to scrolls, which were malleable. You could roll them up. You could, in principle, stuff them in your pocket or your tunic or whatever it was. Books have the same, are soft, flip and stuff like that. When we got to the i-readers, what do you call it, we're back to the rock again, which I even like the picture. It's almost as if you have the two tablets next to each other. So we're now back to the hard object. That's a small thing, but it's one of the things. It's better than carrying around a computer with you, which is kind of awkward. But still, it's a hard thing. It's not something that you can manipulate with your hands. You can't get in and crumple the edge. You can't earmark the edge of a page and flip that the next time, or say, how far in the book am I? And you just look at the book and say, well, I'm halfway through the book. If you're reading the e-reader, it gives you a number at the bottom. It's just, it's a little bit of a loss. There's one other loss in the e-books we have right now, which is how you read them. And this becomes slightly more important. Of course, you saw rock because the sunlight was shining on it, and you can't see, you couldn't read the Ten Commandments on the tablets at night. And the same thing's true about scrolls, and the same thing's true about books. They're all reflective surfaces. When we get to the electronic ones now, they're all emissive devices. So, like the computer screen is giving off light. This is from, my wife says, be sure to say it the right thing. This is the Google version, and this is an emissive display. In other words, it's generating its own light, and so using energy to keep going. This is, as you probably recognize, this is the Kindle, one of the early Kindle readers, and this is a reflective display. So this, you cannot read it at night. You can only read it in the light. And I think if I didn't try this ahead of time, but I think if I hold it up, you can still see the Kindle in the brighter light, and then this one starts to wash out. It even starts to wash out at different angles. And so that begins to make a difference. Well, of course it got dark because I didn't touch it, but let's not worry about that. That was kind of a fixed demo. But in the reader world, the e-reader world, I'm going to make a fuss about the difference between a reflective and an emissive display. So this display is a permanent, almost permanent display. I could pull the batteries out of this, you know this, because once I've moved the image into position, it's stable. It does not require any more energy to do this. So this is very much like a piece of paper, very much like a piece of paper. The pigment you see here is exactly what you see in a piece of paper. And a piece of paper is covered generally with a white coating, usually titania or kaolin clay, and you put down carbon black in the form of an ink, and you make an image. This is carbon black and titania particles making an image. Once they're in position for a long, long time. So you turn this off, and you can see them. Now, the other thing about reading, and I don't like this form because this is still hard, right? But at least it comes close to the kinds of things we're looking at for the easy reading. The kind of your eyes always adjust the intensity of light, so you can see as well on a beach as you can in well, not quite at a moonlit night, But in a moonlit night on the snow out here in Hanover, in any case, there's sometimes enough light to see things. You can start to see at that kind of level. So your eye adjusts to this. This stays the intensity it is. And so obviously when you walk out into the bright sun, you can't see it anymore. You're familiar with that. And so there's fundamentally difference between these readers. And I also want to make a little point about that. The people that are making talk about making e-books and stuff like that, except for this device and a couple of devices you probably haven't seen because they're marketed mostly in Asia, are all light-emitting devices. And there's something about the stable image that is made from the way you would normally read a page. And so I was part of the group that put this thing together. By the way, I'll put in a little plug for those of you who are going to think about going to work sometime, and I suppose most of you are. But in any case, to think about working for small companies, this is startup companies. I went to work for them in 1998. They incorporated in 97. I was the 10th employee. So, and the first 4 were undergraduates from MIT, and they were pretty amazing. But, so there weren't a lot of adults in the room, let me put it that way. As a matter of fact, I'm not sure there was another adult in the room for a while, but you get used to it. It's fun. It's really, really, it's fantastic. Because they were, and I was swept along, absolutely fearless. So we started in 98, and the end of 99, which was about a year and a half later, we had this stuff in JCPenney, in the mall in Marlborough, Massachusetts. No one said you couldn't get to market in 18 months, and we got something out in 18 months. It was in the sporting goods section of JCPenney, and it was putting up the sale signs and stuff like that. And the sign lasted, easily 24 hours before it burned out. And, and so that sent us all scurrying back to the lab and say, what the devil did we do wrong? And that became an interesting experiment. But the audacity of startups is something worth thinking about. When I was your age, if you got a job at Bell Labs, or Xerox Research Center, or IBM's Research Center, or university, you really had the best jobs. These days I'll put a pitch in for the small, audacious, maybe make it kind of world. You are young enough and energetic enough and don't know that some things can't be done enough that you'll find some interesting opportunities. In any case, we got that out very soon. Now, the most important thing that makes me think that even this is not good enough is this idea of browsing. And I'll give you an example of this. So this sounds bad. So don't misinterpret. This is the New York Times book review, right? I read this all the time. No. I never read this stuff. I mean, I read, occasionally you pick it up. I never look at it. But sometimes you pick it up and you flip through some pages and who knows? That's what you mean by browsing. If you want to buy a pair of pants, you go into a big store and you wander around and you look at pants and shirts and stuff. That's browsing. So that is looking at things in a bigger context. And I happen to be reading this, and you won't believe this. So I have it written down here. It says, it's written by a young woman. You always call them young women, of course. At my age, they're all young women in any case. So Anna Holmes, so she says, who or what we choose to read can be as telling as the clothes we wear. Oh, yeah. And she writes down here, browsers may be ubiquitous in our e-portal age, but the e-book doesn't encourage actual browsing. Where did that come from? In the middle. So, and where did it come from? Because I happened to pick this up, and I saw the word e-paper at the top. This is last Sunday, and so this idea of just of looking around, of seeing more than just the thing you asked for, is extraordinarily important. It's a serendipity. It's a serendipity in social issues. It's a serendipity in scientific issues. You go to a seminar, you went into seminars on a subject you know nothing about, you happen to stumble in because you got really good cookies in the background, or you're required to come like this, you stumble in this, you're forced to come here, and you might hear something interesting. It's serendipity. So that's the browsing, looking around at the things you have. And so I was looking for examples of browsing, and I managed to find from your homepage I don't know who this is. A young lady browsing. So she is just in the library looking around. And she may be looking for something very specific, but she's going to see a lot of things along the way. And so I think that's what this kind of Google searching doesn't do. You jump from page to page to page, and you sometimes find what you're looking for, but you don't accidentally read something by a poet someplace that you never would see before. And that would be a big loss. The example of this I find really interesting is this. A fellow, he was an editor of Wired. So Wired magazine, as you probably know, is one of those early techie magazines, and it was generally, this is Kevin Kelly, and this is a little book review of it. I'll let you sort of scan through that, and I'll talk about it. So he's the geek's geek. He was an editor. He created Wired, the magazine. Oh, by the way, I'm thinking about the name of the magazine. This is a small thing. Wired is not the name of any magazine you would ever start today, right? You would write Wireless. Okay, that's just a little aside. So Wired dates Mr. Kelly badly, but nevertheless, okay. So he's doing okay for himself, so we don't worry about it. So what he's saying is that he ran essentially a blog on all kinds of cool tools, things he saw that were interesting, exactly what you would like to have. The kind of thing you sort of pop up and you log on, and a cute thing after one after another. And then one day he had what sounded like, this guy says, a dumb idea. He decided to take the best things he had and make a book out of it. So here are the cool things, cool tools that Kelly identified through the years. And I guarantee you, you are geeky. I can tell who you are from here, that you get hold of this and you're going to go, oh man, look at that. Ooh, look at this. You're going to flip through this thing. You're going to browse through this. And you're going to see things that I saw things in here I can't actually tell you about because in public. But you see all kinds of interesting things on foods and pressure cookers and tape measures and, whoa, can openers. And, you know, the joy of saying, oh, I want to find something in a magazine, and you're looking for something. And on the way, you get things about lanterns and Crank Brothers speed levers. And, you know what I'm talking about? So I'm trying to make the case for having in front of you not that little window that has the one entry you want, but a big window. So think about the New York Times. I'd like to do, and I shouldn't say I'm sure you read newspapers, but when you do read newspapers, you open it out, put it down the table, and there's 20 articles on those pages. And there's an article about what's happening in Central Africa. Who knows I didn't even know where Central African Republic was. But I tell you, by the way, trouble, big trouble. So there's trouble there, and there's Chad, and I don't know where Chad is, but there's a little map on there. And I see a little article about the New England Patriots. That's really important. So I read about the New England Patriots, and then I say, oh, what happened in Chad? And so this idea of looking at a wide span of things, somewhat related, and then looking for the thing you're looking for, but seeing lots around you. Losing this wider education is something we don't want. So what we want to do then is get something that we read that continues this long tradition of being a widely read, a widely exposed person. And if you the thesis is if you sit and just read what happens on the blog you happen to have, or the e-reader, or the Google search you're working way down, you live in a narrow world. And this would enable us to be in the bigger world. So that's the dream. This is the example. This is the kind of example we really want. So in 1998, 99, there were about 2,000 at E-Ink, and by the time we were up to about 50 people by the time we got to the year 2000. Oh, by the way, if you want some fun in your life, there's nothing more fun than hiring 10 or 15 people and having an unlimited budget. So, I say this aside, one time before, when I was not able to hire anybody, when I first went to Xerox, they're selling the 914 copier, which they could not make fast enough for the sales, which, by the way, should never have sold any. We were about the business case for that was completely wrong. They thought only lawyers would buy them. Who else needed a copy, right? So they were selling so many of these things, they were getting so much money, they did not know what to do with the money, so the word went out to spend as much as you can. I was 25 years old, PhD, yeah, such your age, came out of school where they've been niggardly with you. They won't give you a salary much to brag about, and you don't get much equipment, and told to spend as much as you wanted. Nice it was. Okay, but anyway, so we're at the, it's like life is just terrific. I mean, there's so many interesting and happy things happening. There'll be some sad things, but they're anomalies. So it's the good stuff that comes along. So we were at E-Ink. We were not thinking this. No. We had that in mind. And you might have seen the movie Minority Report. It's about a dystopia where the policemen are sent out and they actually arrest people before they committed a crime. Very convenient. And convict them and punish them before they finish the crime. That was anyway, so Tom Cruise is one of the policemen. He's been arresting people and jailing them before they ever did anything. One day he gets turned in as a bad guy, and so they turn on him. This is a scene from a subway ride. Cruise is sitting in the background. He's the hero, of course. Somebody's sitting in the subway. He's reading in the top picture the current day's news. He's reading a newspaper. And suddenly, new news appears, and it appears on his newspaper instantly. And of course, this is where things get exciting. When the guy looks at, this is a wanted man, and over the top of the paper, he sees the wanted man. And so it gets interesting from there. So the vision we had at E-Ink was this, is that you come down in the morning, and the newspaper is today's newspaper. You have one newspaper reader, but overnight it gets updated, or anytime during the day it gets updated all the time. So that was the vision we had. And what we ended up with was this. Not the top of the mountain, right? Coming up the mountain, but so I want to convince you today, we want that. We want the ability to have something that allows us to really browse. No ads in there, no things, no serial things, parallel processing, related things all over the place that, of course, are hooked to the internet and get all the information you want. So the question is, that's not too much to ask. I mean, we went from tablets to scrolls to printed books to iPads. All we want to have is that iPad big and flexible. Oh, by the way, you could make it big, and it's no problem at all. Samsung would love to sell you the equivalent of the iPad that's this big, but it is a little tricky, to walk around with a $40,000 display in front of you. So obviously, we're not going to go from this little thing to a big thing easily. And so what we're talking about doing is going from this little thing. What does it take to go from this little thing to a big thing? And so this is the dream. And so I want to tell you a little bit about what people have done, in case you're not familiar with this field, and probably not. It will not be impressive. Fair game. If I told you to come to work on a problem where we haven't solved the simple problems yet, isn't that the best place to start? I mean, you don't want to go into an industry where they've been, like in the electronics industry, where they've been doing this, they do this stuff really, really, really well and ask you to improve it 0.1% more. No, we're asking you to go think about a problem where we've done really, really, really badly and move us just a little bit further. So this seems to me the kinds of fun opportunities. So let's look and see what you want to do. So the problem is actually easy to state. We want a big, essentially paper-like thing that has an image on the top, and if you want the image to change, then all you have to do is move the stuff that's on the top inside, right? So if I can make a piece of paper, and I could put a print on it, and somehow move the print inside, I just see the paper again. And if I could move that same ink back up to the front in the right order and make a new image, you'd have it, right? So it's a piece of paper with print on it, and all you're asking the ink to do is to move in and move out under control. This is not a sophisticated problem in physics, right? I mean, so you think about in those terms, that's essentially what we're asking for. And so this attempt was an attempt to do that, where we had white pigment and black pigment, and all we did was change the position of the black and white pigment, and I probably shouldn't fool around with this because I'm going to do something stupid, but push the wrong button. Okay, I won't do anything stupid. Actually, I won't do anything at all with this right now. But you change the image. All we're doing is moving pigment in and out of the plane of view. I'm going to talk a little bit about the ink here in just a second and how that differs from other ink. But the big problem, which I will tell you almost nothing about because we know nothing how to do that, we don't know how to make this electronics on the back light and flexible. The big screen that is too heavy to carry around and too awkward is heavy and awkward because the electronics to drive the image is heavy and stiff. And we'll come back to this in just a minute. And there has been, and I hope I don't insult any professors in this room, but there's been no significant progress in making flexible electronics to drive stuff like this. I'll show you the only thing I know I've seen that I thought, ooh, that was pretty cute. All the rest of it is, yeah. I really think, so the printed electronics is going to be a big barrier, but we'll get to that in just a second. We'll talk about how you switch the images. And so this is the simple way to do it. If you have a parallel cell, clear on the top, and a segmented cell, so you can apply voltages at different places. And this was done in the 1960s. I mean, this easily 1960s. It's forever old. Well, I'll show you one here. It was invented by Edwin Land. Edwin Land probably died by the 1960s. And so some of these ideas are really, really old, but still have legs. So the idea is very simple. If you have a colored, this turned to be oil-based systems, a little dye in the oil, and the usual way is to put white pigment on the inside. So if the white pigment is on the front where you can see it, then it's a white spot. If you move the white pigment to the back, then the light goes through the dye layer, hits the white on the back, is reflected, and you see the color of the dye. So just moving white particles from the front to the back will switch between a color and a white state. And that's pretty doggone close to the first picture I showed you a minute ago, where you just take the print from the top down. So this is awkward. There's things that are not good about it, but you can see it's the same general idea. So we're talking about inventions here that are clever, but not deep. You get the sense of what I'm saying? Is you're going to have to think of something really clever, like maybe, I'll do this off the top of my head, maybe you don't have oil in there, you have a kind of a loose pile of furry stuff. And you could get the ink to go down into the furry stuff, technically speaking, of course, and then moving back to the front, fair game. So that would be a furry layer with little black dots on it, and you can move the dots back and forward. So you can see, well, there's ideas like that. So that was the early ideas. At E-Ink, it turns out, by the way, I'll put little things in. If you want something like this that's reflective, you're going to depend upon light shining on it to make an image. If you carry something with a dye in it out into the sunlight, dyes fade very quickly. So there will be no electronic paper. I say these absolutes. I got away with it because I'm going to leave town and you won't be able to contradict me. There will be no electronic papers that contain any dyes because the dyes will always fade in the sunlight. This has to be a pigment-based, at least a pigment-based system. I'll show an exception for that in just a second. So we knew that at E-Ink. That's why they hired me, because they couldn't figure out how to get two kinds of particles that would move independently in the system. And it's a little thing I learned at Xerox for reasons that are not so important right now, but I'd love to drone on and tell you that sometime later. But we learned how to make an ink that was clear oil and black particles and white particles. And I'm trying to remember, the white particles were all negatively charged and the black particles were all positively charged. And the little bit of chemistry that I bring into is I know how to get positive and negative charges in the same liquid at the same time. It's a trick. In any case, it's not a trick. I mean, geez. There's actually some fun science on it. I've been making, for years and years, the lecture circuits on doing something like this. How do you do such a thing? And I get to repeat myself over and over again. We know how to do it. And so here, you just you move the color you want to the front, depends on the charge. So here, you just have black and white particles. If you want the white particles, which are negatively charged, you put a positive potential on the surface and they'll move to the front. And of course, if you have an array of electrodes in the back, you can just flick things back and forth. So that is precisely what's here, as this has a layer of oil The top layer is a coated plastic, an indium tin oxide coated plastic, so it acts as an electrode you can see through. On the back is a patterned set of electrodes, and by controlling all the dots on here, we can pixelate essentially this image and move things back and forth. And so you can, in principle, use this to be the same resolution of this, because this is the same electronics on the back. You have the way of changing the electric potential on each one of the little pixels. In these displays, by the way, you have to put out an AC field because these are liquid crystals, and liquid crystals have to be held into a position, and that holding into position requires constant AC. Here, it's electrophoretic. The particles have to be moved to one spot, and they stick there electrostatically. That's why the image is permanent. As soon as you change the sense of the field, then the particles move back. And so that caught lots of people's attention because it becomes very low power into these things. But 99% of the power goes in the back plane, so that little extra doesn't make much difference, except when you turn off the power. How did I manage to move down? But anyway, so this is did that jump down on me without touching? I must have done something. Did I miss anything really interesting? Can't remember anymore. No, nothing interesting. Okay, so we move on. Now I want to give you just some examples. So I'm trying to tease you. I'm trying to tease you to say, look at that guy. He's showing us these really simple things, and you haven't made electronic paper yet. I want you to think that this is an easy job, okay? That you will spend the next few months thinking about this, and you will make the brilliant invention, and we'll all clap and give you an award. I really want you to believe this. I, of course, don't believe it. I don't, But this was really important. I'll tell you how much I believe in it right now, though. By the way, as a little aside, is that a few years ago, Harvard asked me to come teach some classes. It's pretty much like Dartmouth coming to teach some classes when you're just a guy working someplace. You don't say no, right? It says, the Vatican calls, the Pope would like to speak with you, please. So yeah. So I went. But it was to lecture, and I had time to do something else. And the time I have been spending the last 5 or 6 years is on this problem, by the way. So if you are interested in it, let's talk a little bit. All right, I'll come back to that in just a second. But here's another example. So this is an example actually done at Xerox PARC. Instead of moving particles back and forth, why not just rotate the particles? Oh, that is a sweet idea. So you make particles that are black on one side, white on another side. Nice materials engineering, nice engineering problem. I say this is engineering, and the reason I put engineering in the beginning was there's lots of ways to define an engineering problem. But an engineering problem to me is you know where you want to be, you just don't know how to get there, right? So that's a little bit different than sort of exploratory science where you say, I look in a room and say, hey, what's in here, right? So this is a crude way of saying it. So the reason I'm happy to pick engineers because I think you've identified yourselves as people that say, give me something hard to do and I'm going to figure out a way to do it and make a lot of money as I go, right? So these are just examples. So how you make particles are black on one side and white on the other. It turns out to be non-trivial. We'll talk about that right now. But they can be made. How you put them in little holes in plastic and put one in each hole is a tricky bit too, okay? But we won't worry about that. It's been done. You see there's levels of stuff. How to make them positively charged on one side and negatively charged on the other? Well, I figured out how to do that before because I showed it to you earlier. And then you make a coating of these. So there's a lot of invention in this, and it's beautiful because it would be bistable. So you flip things back and you get an image. So this would be really interesting. And so you build something like this and you make a big fuss about it. But the guys who did and gals who did it realized that it's not useful from the very, very early days because they had to do a little bit of physics. And the physics is how do you turn a particle all the way around and stop? And the electric field is very strong. Field is very strong, but as you begin to line up, the electric field the force goes to zero. And so it means it's unstable. You try to switch, you go too far. And so it turns out you can't get all the balls to switch black and then back to white. You get some black and some white. So it's really tricky. Now, that's just to say that someone in this room says, I know how to do that. I just change the rheology of the liquid, and I get a yield point, yada, 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 and off you go. And that's what we want. Someone to say, oh, yeah, I got a better way to do it. Turns out, There's a couple other small inventions along the way. One is this, which is don't move the particles front to back, move them side to side. And side to side, they have less distance to go, so it's much faster. And you could convince yourself that this is a system that actually has 3 levels of color. So if you had a white particle and a dye, and you could make it go from black by pulling the white particles back into one corner with a black background. You can make it white by putting all the white particles on the front, and you can make it a dye by putting all the white particles across the top of the black background. So here, with one set of particles, you can generate 3 kinds of colors. And so you get interested, oh, and then how do I get color? And that's a little bit of the story I'll tell you in just a second. That's what keeps me still in the game. There's another thing you can do, and is that if the spheres don't work, this is, I think, the older invention. Oh, yeah, so this is Land, who went on to make the instant camera. It's sad. We should have a moment of silence, because Edwin Land was one of the geniuses of all times in invention. And we've outgrown most of the inventions. You know, it seems like I remember, I see some gray hairs out here. I remember when they sold the instant color camera. I forget it was something 70. We took it in the lab, and every experiment we did, we took an instant picture of it and stuck it in our notebooks. It was the height of technology. Now, of course, you whip out an iPhone, you take a picture of it, you send it to your thesis advisor, and it's nothing. In the old days, this was like unbelievable magic. Anyway, he had this idea. You don't take spheres and turn them. You take rods and straighten them out, which is easier to do. And so you can have a system where light goes through or light is blocked. So there's lots of ways to move particles around, either by shape or charges and things like that. And so
They still have polarizers.
well, they still have polarizers. They still sell the film. Oh, that's good to know. You know, I hope they're getting a good annuity from this. So. But unbelievable. Oh, by the way, which you didn't come here for advice. Okay, another piece of advice, since you say there's still something left. First thing is startups never die, because the people that are in them will not give up until they're starving to death, which is a long time. So, and you don't have to stay quite to starvation, right? So it's no danger for you to go take a job at a company that has no more money than will last 1 year. After all, in lots of places, you work on a project for 1 year and you're bored. So 1 year is nothing. So don't worry about going someplace that can't guarantee you retirement. Forget retirement. Oh, by the way, there'd be no retirement for your generation. It's long. You might as well work until you drop to the ground in a little silly mess. That's good news, I guess. I don't know. But don't worry about longevity at places. I've talked to some people here. I've worked at IBM and I worked at Xerox. We live in Rochester, New York. Kodak was there. Kodak. In the 1990s, when we were there, Kodak had 55,000 people working in Rochester, New York. They were smart, well-dressed, educated, beautiful children, lived in the suburbs. It was fantastic. And now there are nada employees of Kodak in Rochester, New York. They're all gone to the wind. Gone. And so much for longevity. Don't worry about taking a chance. I mean, you're going to get fired eventually anyway. So, take it like a man, or take it like a woman. No, take it like a woman. They do a lot better, I think. But nevertheless, so off they go. Now, there's some other ways to make the images, and so these are in production or being sold. And I want to show you to this kind of thinking, so you know. So just remember that all the devices you see that are sold as readers these days, except for this guy, most of the ones you see are exactly this guy. Oh, why doesn't it start when I open it up? Please. Oh, there it goes. I guess the right time. Oh, I have 14 minutes to go. That's useful to know. 17 more slides, 14 minutes. Okay, no big deal. So, but there are some other ways to make images, and these are things that are actually in the market now. We don't see in the US of A. And the first one I wanted to show, these are done with cholesteric liquid crystals, and of course these are stolen off.
Substrate, bottom substrate, there's black paint on the bottom.
Can you hear it?
The molecules are oriented generally horizontal to the surface of the display. And in that orientation, you see black. Because what happens is, light goes through the top substrate to the liquid crystal material and is absorbed by the backbone. Okay? If I apply pressure, I cause the molecules to stand to attention or perpendicular to the surface of the display. Light strikes it and then is reflected back at you. And then to knock these back over on their side, I need electrode.
Enough is enough. So these Kent displays are sold in large quantities, and you won't see them in this country. The contrast is quite low. So they have liquid crystals. So these displays are all liquid crystal displays, right? The reason they consume so much power is that there's layers of liquid crystals and layers of polarizers. And so on the back of this is not gigantic, of course, not gigantic, a white light this size of gigantic power to light. So this is probably emitting maybe 5% of the light generated. 95% of the light is lost inside here, shining through this very inefficient layer. And so these are all liquid crystal displays, and they're high power because of that. And they're not stable because as soon as you throw them into the field. So you have to have a really bright light behind them, and you're using only a small portion of the light. When E-ink came out with what they call the bright white, what they did was to put a layer on the top around the edges that emitted light. So they put a small light bulb, essentially, inside this to make it brighter. It's not brighter because of any change in the physics. It's brighter because they put in a current-using device, but not a very bright one in these things. Well, we're anticipating that if you go to something big, it's going to have to be completely from the edge, from just reflected light. The only reason ITRI is the research labs in Taiwan. I have a bunch of friends over there, a number of them from Xerox and Kodak, who, after these companies fell to their knees, found work over there. Which is to say, something it's sort of interesting is on it's funding. Is that some countries, and I mean this in a very positive way, invest a lot. The government invests a lot into research and then hands the research over, kind of thing. We don't have that kind of. We're searching for models here about how do you get funding in the hands of people that are really smart. Oh, by the way, you are the people that are really smart. So how do we get money into your hands? And we do it by making you work very, very hard as graduate students and actually not paying you very much. The same thing's true with postdocs. They get paid a little bit more, but yeah. Right. Okay, so that's the funding model right now. It doesn't seem to me to be the best possible funding model. It would be nice to fund smart people long enough to do something other than publish 3 PRL letters and then take off for another postdoc. But that's just my opinion. And I've learned that my opinion is it does not need to be well known. Anyway, they've learned how to make these colosteric coatings like they have on the Kent displays in long strips. And so they're actually making scrolls now. So it's the width of a coater. It's a backplane with electrodes on it that you can address, and then the polymer layer, and then the ITO top coating. And in this case, the fellow said that you get an image by putting pressure, and it aligns the liquid crystals and it holds a permanent image. And to erase it, he erases it with a little bit of an electric field. I liked it because it was a scroll. And so imagine, wouldn't this be interesting if you got the electronic paper which you develop and find out that the best format for it is in a scroll? It would seem to me to be so poetic, I would buy it immediately, even if I could never use it. It's just sometimes you just have to do things for the beauty of it, right? So I would love the first electronic book to be a scroll. Oh, and I would like to have the 10 Commandments on the first page. That would be really good. But in any case, yeah. Now, there is a set of technology that people are working on now that I wanted to mention as we get closer to the end here, and that's electrowetting. And this is just a drop of water, and all you're doing is changing the electric potential in the oil, in the water in this case, and the water drops moving back and forth. This is what we talk about in soft matter classes. You know, what's the scaling law for stuff like this stuff. Anyway, you could probably get the general ideas that the electric field builds up on the substrate that lowers the energy, and the system spreads a little bit, and it's completely reversible. So when I saw this at first, I thought, wow, that's neat. because you can do a little scaling, and where's Dr. Ron here simply? Oh yeah, scaling, see this man. Every problem should start with formulate the problem and then write down the scale factor. Does this take a tenth of a volt, 10 volts, 1,000 volts? Makes a big difference before you start working. Okay, it turns out this takes volts, maybe 10, marginally useful. In any case, so the drop spreads. It turns out if that were a drop of color, you'd be moving a lot of color over a reasonable distance in a short time, which is to say you can make an image very fast if the liquid were small. And that's exactly what's fine. These things work way past video speed. You move the drop really, really fast. And if you think about it for a while, if you're moving particles through a liquid, there's a big drag. If you move a drop through air or through another liquid, there's a lot less drag per unit color. Odd way to scale things. And anyway, this sort of interested me. So when I got this call from Harvard to say, could you come down and teach? And I wanted to do that because it just was, it's glorious to be with a bunch of students, postdocs and graduate students, undergraduates. It's like, oh, I don't know. I love it. It's just, you never know what they say. In any case, some of it actually reasonable. Not a lot, but but all amusing. In any case, I decided that I would work on the display, and for me, the most important thing was how, whatever I did, it had to be in color. There's no reason to make a display, even for electronic applications, that wasn't color. And so I sat down and thought about how you move lots of particles around by electric fields. And after about a year and a half, I finally came up with something that looked like it would work. And I did the scaling laws and said, yeah, if you didn't mind it changing its image every 10 or 15 seconds, which is not quite video speed, you could do it. And then I was called up by some people saying, oh, have you ever looked at this electrowetting business? And the answer was no. And let me show you this one first. This is taken off the ITRI site. There's a little bit of a beginning. And this is a display they made with electrowetting a few years ago. And something should appear. It's not appearing. Oh, there's something there, right? Somebody read what it says. It's not going anywhere, is it? Do it again? Oh, jeez. And then I'm used to having, so the music plays, forget about this. You don't care about how they make, I just want to show you the top of it. So these are liquid. Now the first switch, and not so good, huh? What they're doing is pulling all the color into a corner. And they have what? Red, blue, green, and black. And then you get white. So all you need to make a display is 3 colors, black and white. So this has all the possible, and these are drops moving across into a little cell and then moving to one edge. You get the general idea. Definitely can go video speed. So I said, all right, I'm going to work on making these systems for displays. Those guys are working on it too, but I have a slightly different attitude. My attitude is it has to be pigment-based, and doing this in pigment-based is tricky. And I'm down in my basement concocting stuff. I may or may not make it, who knows. But this is a little different. This is so ITRI's working on this. University of Cincinnati, if you're interested in displays, and the oddest places. Not that Cincinnati's odd, but it's not usually on the tourist list. But never. Okay, I won't say about Hanover, but nevertheless. So this is the same idea. The liquid is being pulled down into a hole. So this is actually it's red, I think, and so the liquid's going down into a hole, and I'll show you here in just a second. They call it pigment, but they're not actually, don't mean this. And so this is what it looks like when it goes down a hole, it comes back and forth. And so it says, if you work with a liquid, then you can do that little dance about putting things in different places in the back. And so you can imagine 4 wells and 1 display, and you just run up any ink you want at whatever speed. So that's beginning to sound good to me. And so it's beginning to sound that will make reasonable progress. But there's 1 or 2 other things I want to tell you, and then I have to stop. This is a technology that's made by Qualcomm, and this is completely different, and I thought you should see it. So in each cell, there is a very small gap, and you can change the gap. This is done by interference, And if you did Snell's law, and oh, by the way, and back to scaling things. So how thick, roughly, is the gap between these two things? You're doing Snell's law and getting refraction for light at the visible wavelengths. You could figure out for yourself how thick that has to be, and you change the gap. When you change the gap, you can change the color that's on the system. You can go from black, which would be the light just disappears inside, to being totally reflective at different wavelengths. And so I don't have a video of this. And this is made and sold, but not sold in the United States, as far as I know. So this, that's not true. On Google, Amazon. I get those confused, but I suspect they're different companies. In any case, but I don't use any other company, so you go on the web. It's either in Google or Amazon, and you either want to find out about it or buy it. And anyway, so you can get these little watches. It's a mere $600, so it's not too bad. All right, now, one last thing. All those things are saying we're making some small advances on the inks. So we probably have we could convince ourselves that we might be able to get, say, electrowetting to make lots of colors at sufficient speeds, and that's probably manufacturable in little, you can imagine making little cells, little micro this and micro that, fluidic stuff. But now the electronics. And I said at the beginning, the electronics is really where we've made almost no progress. I say that because every week in the Harvard Gazette, which I get every morning, and I read, of course, from beginning to end, we have cured cancer and heart disease and poverty repeatedly. Okay, we've also made printed electronics so many times, but of course they don't work. And so making printed, and the reason making printed electronics is hard is that transistors depend upon gaps in the conduction bands, and those are exquisitely sensitive to thicknesses and compositions, and so those are not things that can be made casually. They are extraordinarily precise objects. And to think that you could do a coating on top of a coating and drop a drop and put an electrode and get something that had the properties of a transistor is going to be a huge problem. So we have to figure out how to get the signals to the back of all those electrodes with electronics you can move. And I wanted to finish today's talk off and say, I have no idea, but the only idea I've seen that I really, really like, I wish I had thought of it, was this, is that in the electronic board, there is a little bit of electronics that has to drive what happens behind each pixel. But that electronics is actually small compared to the size of the pixel. So the bit you need to drive things, in its essence, is tiny. Yet you have this big piece of quartz or whatever you build the silicon, you build the backplane on, just to get that one little bit every now and then. So what happens if you took that little bit every now and then and think about, suppose I just took the little circuits, these tiny circuits that would be maybe a micron by a micron at most, and I could wire them in with little flexible wires. Well, that seems tricky, and it turns out that a company called Alien Technology, I swear, it really, one of the hands, I forget. You have to lift one right hand or put it on your heart. I can never remember. I had to visit a judge the other day. I didn't know whether I was swearing in or, anyway, so I'm still waiting for the results of the court decision. I'm not optimistic because I was doing this to the judge for quite a while. And I was scared to death. But anyway, so this company had this incredible idea called Alien Technology. It had to be from the West Coast, of course. On the East Coast, we'd call it Smith Enterprises. But on the West Coast, what they said was, I got this great idea. I will take a piece of plastic. I will put down the wires that I need on it. And that we can print wires pretty doggone well. How do I put the little bit of electronics at the right spot? And the answer is, you put a little hole where the transistor could be. And if you have different kind of transistors, you can make different size holes. I put these little circuits in a bucket of water. God is my witness. It's true. They put it in a bucket of water, and you let the water slide across the plane. And you can arrange the conditions so the little bit of electronics fall exactly where they're supposed to be all the way across the sheet. And I searched high and low to get the video that shows you this, but this is just a picture of it all. This doesn't help much, does it? You know, I can throw it up there. But I got one shot, and I missed So these little squares are popping into the ball, and those little squares contain all the smarts, and then there's the wires between them. So this is a flexible display. And they went the way of most startups, which is you are bought by venture capitalists. Venture capitalists want to make money as soon as possible. This will kill your enthusiasm, but get over it. They want to make money as fast as possible. The fastest possible way they can make money with this technology was in RFID tags. And RFID tags are what you all know about. They have to be one thing and one thing only. It's really, really, really important. Damn cheap. And they can make them cheap that way, and so they do this kind of technology. Eventually, they'll come back and say, oh, maybe we should make an electronic newspaper. But they're busy selling off these RFID tags. So I told you that at the beginning, this is sort of illiterate, and so I have a little limerick for us. Here I come, greater than the tablet, All there is to know, I know it. Because we want this electronic paper to be online, of course. I shall show it in a great collage. That is to say, I want a big thing. I want information all over the place I can and it browsed with pleasure and knowledge. So for our friend Joe at the beginning, we make a little bit. And so I've taken out the lost dream because I have faith in you all. This is a midwinter's afternoon's dream. It's not a life dream. So I hope someone takes the mantle and goes for it. Thank you very much. Stop right there. Next.
I have 3 comments to make. The first is getting into Hanover, you go downhill for quite a ways.
Oh, I missed that part.
You can New London.
Oh, New London, oh, I see. I was so excited I missed it, I missed it. Okay.
Secondly, you were very eloquent about the need for paper. And there's an excellent book, if you're interested in this topic, that you may not know of, called the Gutenberg Elegies.
Oh, no.
Gutenberg of the Gutenberg Bible, the Gutenberg Elegies. I'm sorry I don't remember the name now of the author. He's a professor of English at Middlebury College. And this was actually written in 1999, I believe, or early 2000. So it's quite old, but he said much of what you're saying.
Oh, okay. He must be a smart guy. Okay, good. Write this down.
And thirdly, I just wanted to tell you that once I was actually funded by the military to think about how we could replace paper. Their particular interest was that a person on the battlefield, a general or whoever goes on the battlefield, I guess generals don't, it would download from the whatever, a GPS, let's say, and want to make it into a map. How would he get it onto a map? So the whole question was, could we come up with an electronic way to take that material and put it on something? By the time we asked him what that something could be, I realized how magic paper was. He could, literally stuff it into a military pocket. He could, I suppose, make layers of it and put it here and save its life. It could get wet in the jungle and dry out. It could get cold in the Arctic and dry out. So there's a long way to go before paper. Paper is an absolute magic.
Yes, it really is. That's right. Thank you.
When people envision the electronic newspaper, do they envision something that would be like 3 or 4 pages or 20 pages?
Yeah, that's an interesting question. I forgot to bring this up. So this is probably too big for an electric book, so you wouldn't want. But I wonder if the 10 or 20 page is enough because it could update itself as you move through. So my guess is that we'll do pretty well with 1 or 2 pages to start off with. A book wouldn't have to be too big.
There's probably some room in the binding for electronics.
Yes.
And that might be a place to start. It's not perfect, but a place to start.
Right. Yes, sir.
Just out of curiosity, at Bell Labs, we built the 1980s version of the Minority Report. could specify what categories of news you wanted. Have it downloaded to your house in the morning. You could have it updated. You could specify health, business, random, and it would be all downloaded, of course, by AT&T's long-distance network, for which you pay. There were several problems with that, however, in 1980. The download speed was slow, and the dot matrix printer was so loud I had to put it in the garage.
Shh, dot matrix printer, they don't know about this.
Newspaper.
Yeah. But yeah, we will not give up the knowledge flow. That's turned on. We want to keep that going. I mean, the volume. Yeah, thank you. Yes, sir.
How do you feel about the possible solution of projection rather than having it there on itself? I've seen examples of where you wear a small device around your neck, and everything can be then transmitted to that and then projected onto whatever you might be holding in front of you, or on a wall, or on the table in front of you. Would that serve essentially the same purpose?
I don't know. That's an interesting question. If you could just hold a white sheet up and that's
Any white sheet. Throw it out, and when you're done, and get another white sheet. It could be.
Yeah, that's interesting. That.
Same point, the keypad that is not there, project to.
The MIT Media Lab is doing a bunch of stuff in that.
Heads-up display on any airplane.
Yeah.
Heads-up display on any airplane. Doing what you want, it should be flexible. It's plastic. The same thought.
I invite you to speak with Ian Morrison if you have more questions. Thank you, Ian.
Hey, Jane.
I enjoyed that. That was really nice.
You can take the equations.
Do you know how to get to where we are?
We're still on? We're all set? Excellent. No, I don't. Did you run into Barbara at the back? She's right in the back, and she's in the middle in the back, and the pink. Let me close this down. I'll be right there. Yeah.
I'll be in touch.
Oh, excellent.
We'll see each other again.
Yeah, at the very least, we should try to make some particles in nano.